Let's get started. Yeah, so today we will continue on embeddings. The homework that's currently out, I think, is due Wednesday, and the programming assignment. There's no class next week because I will be away, but the programming assignment will be due in the end of the week next week, and you have 2 extra days to do that past the deadline. But we'll just put out like the next one when the current one is due. Is everybody able to run the starter code for the programming assignment? Have people tried to do that? All good? Okay, great. Yeah, if you haven't tried to do that, I suggest at least you try to run the template code. We gave like the testing scripts, and you have to fill out a bunch of functions in there. So just make sure that it runs for you. And yeah, we're just going to run on the cluster like last time. Okay. So just to recap, we're going to continue embeddings. So last time we were doing embedding, and basically what we're going to do is this. We have a target topology, which is the topology that we actually have in our machine. So when we have like a distributed memory computer, the nodes have to be connected by some kind of topology. Like we cannot, in practice, it's not possible to have an all-connected network, which means that all the nodes are connected to each other to have direct send and receive, because as the number of nodes grows large, that takes n squared links, and it's physically hard to do that. So usually we have different types of topologies that are available to us. And one that we have been doing for a while is hypercubic topologies that can route hypercubic permutations. So we're going to have that as our target topology. But for some algorithms, suppose that you have an algorithm designed for some source topology that is not the hypercube. Like for example, for matrix algorithms, it's often easier to think about the topology as a grid because the matrix can be cut up into a grid. So suppose that we have a matrix algorithm designed for suppose that we have an algorithm designed for something like a grid or some other topology, and we actually have a hypercube, and we want to run the algorithm on the hypercube as efficiently as it was in the original source topology. And that's the point of embeddings. We're going to represent the machines as graphs. So the nodes are the compute nodes, and the edges are the direct connections between them. And we want to directly map. So we don't want to actually we don't want to redesign the algorithm for every single topology. Instead, what we're going to do is try to provide some function between the two underlying graph topologies of the networks. So we can just directly run the original algorithm through some mapping of the nodes and edges. So that's the high level goal of where we're going to go. And yeah, both source and target are modeled as graphs. So we had these performance metrics. I'm not going to go over them again because we just did that last time. And the mapping is a special case of embedding where all the performance metrics, like the ones related to nodes and edges, are all 1, which means that there's a one-to-one mapping between the nodes, and there's also a one-to-one mapping between the edges. One thing that is a bit hard to get sometimes is the direction of this mapping. So the target topology is a hypercube, and we logically have some source topology that we have a designed algorithm on. They may not have the same number of edges. Like for example, last time we're going to continue, but we're trying to embed a ring into a hypercube. And as the number of nodes grows large, like the number of edges in a ring is less than the number of edges in the hypercube, because for a d-bit string, the hypercube has 2 to the d nodes, and each one of them has degree log d. But every node in the array or ring has at most 2 degree. So it's clear to see, like as d grows larger, the degree of the hypercube is larger than the degree of the array. But that's okay, because the source is the array, and we're trying to map it into the hypercube. So it's fine if there are fewer edges in the source. There's a problem if there are fewer edges in the target, because then you have to map 2 edges of the source into 1 edge in the target. Yeah, so that's just something to keep in mind when we're doing embeddings, is like to be clear about the direction that we're trying to go in. Any questions? So we were here last time. Suppose that we have an algorithm designed for either an array or a ring. So an array is just this, where we have a bunch of nodes and each of them they're all connected in a line. And a ring is very similar to an array, just that the last one is linked to the first one. But an array, there's no link from the last to the first. And we're trying to embed this ring into the hypercube. And if we have an embedding for the ring into the hypercube, an array is just a subset of that. So we're just going to focus on the case of ring. So suppose we have these nodes in the ring labeled 0, 1, 2, 3, 4, 5, 6, 7. And in the hypercube, remember that every node can be described, if you have d bits, every node can be described by this d-bit string, and all the connections to that node differ in 1 bit. So your neighbors are just 1 bit away from you in the hypercube. So basically what we're trying to do is we're trying to map the neighbors of the ring into neighbors of the hypercube. And so why can't we just directly map the source ranks into the target ranks? Well, in the ring, not all of the neighbors differ by 1 bit. Like, for example, 3 and 4 differ by 2 bits. Like 3 is 1, 1, and 4 is 1, 0, 0. So that differs by actually 3 bits. So just directly mapping 3 into 3 and 4 into 4 is not going to work, because, like, if you have it, suppose that you have an algorithm that runs on the ring, and you expect 3 communicating to 4 to take 1 hop. But if you map those directly into the hypercube, just 3 to 3 and 4 to 4, it's going to take 3 hops because they differ by 3 bits. So this is the direction of the embedding, and we're trying to preserve this property that the neighbors in the ring also are neighbors in the hypercube. So that's why we need to change the index. And so we're going to change the indices in the ring to indices in the hypercube, where each of them differs only by 1 bit with their neighbor. So this is the assignment. This is one possible assignment. So 0 and 1 stay the same, just 0 and 1. 2 goes to 3, 3 goes to 2. So those also differ in 1 bit. And notice that 1 and 3 also differ in 1 bit from each other. So like 1 is just 1, 3 is 1, 1. And in the second half, 4 goes to 6, 5 goes to 7. Those also are only 1 bit away from each other. And 2 and 6 are also only 1 bit away from each other. The top bit gets flipped. And we have a similar story. Like this is 5 and 4. 7 is 1 bit away from 5. 5 is 1 bit away from 4. So in a moment, I'm going to show you actually how to generate this, but this is just one example. And the high-level idea is that we want to generate such a sequence where all the numbers in the sequence differ by only 1 bit from the one right before and the one right after. And that would give us an embedding into the hypercube. So we can use gray codes. And gray codes are this binary encoding where 2 successive gray codes differ by only 1 bit from each other. And there are many different kinds of gray codes, but this is one possible generation. So the binary codes just go up normally, like 0, 1, 2, 3, 4, so on like that. And each binary code maps into some gray code. And the ordering of the gray codes is not the same as the ordering of the binary codes, but they have this property that they change only by 1 bit as you go 1 by 1. So like here, 0, 1, and then now this is 3 rather than 2, because 3 is 1 bit away from 1, 2 after 3, because 2 is 1 bit away from 3, and some others after that. So this is just the assignment that we had in the previous slide. Questions? Yeah, so how are we going to generate them? Well, one pretty straightforward way to generate them is called binary reflected gray code. And you can just generate them recursively. So the base case is p equals to 2. And for p equals to 2, we only have 1 bit because there's only 2 options. So they are 0 and 1. And of course, they differ by 1 bit because there's only 1 bit. So that's the base case. And for p equals to 4, to go to the next case, imagine like a horizontal line halfway through, and you reflect the previous gray code from. So suppose that we're trying to generate a gray code for p processors, and we have the gray codes for p over 2 processors because we generated them through this game. The way to generate for p is you draw a line at p over 2, you reflect what you had for p over 2 across this logical line, and you flip the top bit. So the top bit in the first half is 0, and the top bit in the second half is 1. So this is an example for p equals to 4. So the base case is just 0 and 1. And imagine this kind of like horizontal line here. So the lower bits are 0 and 1, and we reflect the lower bits across this horizontal line. So it becomes 1 and 0. So it's like 0, 1, 1, 0. And the top bit in the first half is 0, and the top bit in the second half is 1. So you need to set the top bit because just reflecting them, just reflecting the top half is going to not, you need all unique integers in the mapping. Like every node in the source needs to map to one node in the destination. It needs to map to a distinct node in the destination. But if you just reflect it without setting this top bit, then you're going to get doubles. So the scheme will cover the entire space of numbers with d bits, and it will also preserve the gray code property that they all differ by 1 bit. Um, is it clear that it preserves the gray code property? Yes. So draw a line at p equals p. So suppose you have p over 2. You have already generated the gray code for p over 2, and you want to generate for p. Putting a 0 in the top bit for the first p over 2 is the same, because like a number is the same if you put a 0, just one more in the most significant bit. But now you need to cover twice the range of the binary numbers. So that's why you set the top bit. Does that make sense? Like one way to think, just in general for binary numbers, like if you have d binary bits, and you think of it like you have a way to generate the code for d minus 1 bits, then you just need to you copy the d minus 1 bits sequence twice, and half of them have 0 in the top bit and half of them have 1 in the top bit. Why does this preserve the gray code property? Yes. Mhm, mhm. Yes, exactly. Yes, great. So the reason that it preserves this property is exactly as you said. If you know that the first p over 2 have the property, then you reflect it. And so you would know that the lower bits in the second half also have this property because it's just flipped. And then, so the only case that remains to be shown is this middle case, like right before and right after the reflection. And that's why it needs to be flipped, because like the lower bits are the same right after and before the reflection, but we flip the top bit 0 to 1. So now that part also only differs in 1 bit. Great. Exactly. And so we just can repeat the scheme for arbitrary p, or for arbitrary p for powers of 2 by doing the same thing. We take this line now, so like if p equals to 8, we draw a line at p equals to 4, we copy what we had for p equals to 4 here, we set the top bit to 0, and we can flip the entire sequence over the reflection line. So 0, 0, 0, 1, 1, 1, 1, 0. And now 1, 0 gets flipped over here because the line is here. And then just flip them like 1, 1, 0, 1, 0, 0. And the lower half has the top bit set, and sorry, the lower half has the 0 in the top bit. The upper half has 1 in the top bit. Yeah, and you can repeat this for any power of 2. Like if p was 16, then you would just do the same thing, but draw the horizontal line here. Questions? Yes. Okay. So yeah, so you can just define this recursively. You can embed any array. So we were trying to embed the ring or array into the hypercube. And if we have 2 to the d nodes in the array or ring, 0 up to 2 to the d minus 1, we can embed that into a d-dimensional hypercube using these binary reflected gray codes. And this function gid, I is the index, d is the dimension, or like d is the length of the bit string. The base case is 1 bit. The index at 0 is 0, the index at 1 is 1. And if we want to go to one more dimension, so x plus 1, and we have some index, the first half is just the same, because that's like we just copied the first half before the reflection line. And this is the second half. So this is like going backwards, just in the first half. So it's defined recursively in the x dimension, but the index is just going backwards rather than forwards. And this 2 to the x means setting the top bit. So that's how you generate it. Yeah, and the reason that we were doing, oh, you have a question? Yes. What are these bounds? Oh, this is for index less than 2 to the x. So if we're trying to go for dimension x plus 1, 2 to the x is just the first half, and after 2 to the x is the second half. Yes. Yeah, this is the reflected part. So this is the reflected part because it's like, as I is going up, this thing is going down. And it's defined in on the x dimension. So this is just saying the lower bits, and this is saying the top bit is 1. Any other questions? Yeah, so now with this binary reflected gray code, we have this property that if you map any, like the array is just numbered 0 up to the d minus 1, that do this mapping, and any 2 neighbors in the array after the mapping are also neighbors in the hypercube. And remember, the direction that we're trying to go, like there are fewer, as d grows large, there are fewer links in the array as in the hypercube, but that's okay because the direction that we're trying to go, we're trying to map the array into the hypercube. So we just need to show that we don't lose anything in the mapping from the point of view of array. Like any algorithm that we had on the ring, using this mapping is going to run in the same time on the hypercube. Yep. So we have these properties. What is the congestion, dilation, expansion, and load? We can start with the first two. So congestion and dilation have to do with edge properties. Congestion is if 2 edges from the source map into 1 edge from the disk, then the congestion would become 2 because if you try to send along that edge, they have to wait. And dilation is if 1 edge becomes 2 in 1 edge in the source becomes 2 edges in the target. Mm-hmm. Go ahead. Congestion, I guess would probably go down. It would go down. It can't go down less than 1. Yeah, it would decrease, but it would be because like in network topology, it's like all of vertices that are connected by an edge are all technically within one processor. So you wouldn't have to move as much as you wouldn't. So if you were moving data between those processors, you wouldn't have to whenever you had to access like a processor that was outside of like that certain processor, it wouldn't have to go through the traffic. Let me see if I can understand this. So it wouldn't have to go through as much traffic. Could you say it again? Why? I guess what I'm thinking of I guess by mapping the topology is that like certain logical processors, more than one logical processor is actually like a physical processor, and since it's a linear ring, that means only one edge connects those logical processors. I see. For our purposes, it's a good point. For our purposes, we can assume that each logical processor is actually one physical processor. Yeah. Yes, good point. So, yes, sometimes with added complication, you can have more than one logical process per physical processor, but for simplicity, we will just say that each logical processor is one physical processor. So to calculate things like congestion and dilation, we have to look at the edge properties. So like we map the nodes onto we map the nodes of the array onto nodes of the hypercube. And let's go back to this. So we can look at this mapping, and to reason about the edge properties, we just look at neighbors in this mapping, and if these edges, so like there is an edge in the hypercube, for example, between 0, 1, 0 and 1, 1, 0, and also similarly, like there's an edge in the hypercube between any of these two neighbors. Congestion would become more than one if these edges were non-distinct edges, because if two edges in the source map to one edge in the target, then the congestion would become more than one. So going back to this, so the congestion is like a factor off the original, it's like a multiplicative factor off the original source topology. Oh, sorry, yeah. So the question is like, how is the congestion affected by this mapping? Are multiple edges mapped to the same edge in the target? You're shaking your head no. Yeah, go ahead. Could you say more? Yes, exactly. So none of the edges are mapped to more than one edge. Like each distinct edge in the source is mapped to a distinct edge in the target. And similar for expansion, dilation, each edge in the source is mapped to one edge in the target. Because you may have some embeddings where an edge in the source is mapped to two edges, like a path in the target with at least two edges. But in this case, they're just one-to-one, so the properties are one. And from the node mappings, we had load and dilation, which is like, are there more nodes in the source? Or like, what is the number of nodes in the source related to the number of nodes in the target? And here, there's an equal number of nodes in the source and the target, because we have this d-dimensional space, and we cover the entire 2 to the d space. So yeah, so they're all one in this mapping. And like I said, to get to this, it doesn't matter how many links there actually are in the target. Like there are more links in the hypercube. Yes, please go ahead. Yeah, so you're saying like in the hypercube, there's actually like between 0, there's actually like 1, 2, and 4. Yes, we can use we're using a subset of the links in the embedding, but it's like in the direction that we're going, we're trying to reason about like how many links in the source are mapped to links in the embedding or distinct links in the embedding. So congestion would become greater than 1 if 2 links in the source were mapped to 1 link in the target. Yeah, so it wouldn't work. So if you try to go back, if the source is the hypercube and the target is the ring, you may get congestion greater than 1 because there are more links in the hypercube than in the ring. So like if you're trying to map all the edges, some edges are going to be overloaded in the target. Yeah, so it's just because of the direction that we're going in that they happen to be one-to-one. Any other questions on this part? Yeah, so this is just an example. So we have these gray codes. For 1 bit, it's just 0, 0 and 1. For 2 bits, the lower ones are 0 and 1. We reflect it across this axis, becomes 1, 0. The lower bits are set to 0, the top ones are set to 1. And for 8, for p equals to 8, we have 3-bit gray codes. generated in the same way, and those map to these hypercube ranks. Yeah, and these edges are actually like the ring edges that are mapped in, but you can see like not all the edges are accounted for. Not all hypercube edges are accounted for in this embedding, and that's okay. Just all the ring edges need to be accounted for. Yeah, so this is just the same function, embedding the ring to the hypercube. Suppose we have this function, gray to binary. Yeah, so this is going the opposite. No, this is going in the same direction. You're embedding the ring into the hypercube. And yeah, so the left neighbor. So you have this function, gray to binary, of the ring, and this is just going to give you back. So to go from the ring to the hypercube, you have binary to gray, like in the same mapping that we just had. To go back, you have gray to binary, and you can just go back and forth between them because like when you generate them, you have the mapping. One side is just the binary in the original order, and one half is the gray codes generated by this reflective scheme. Yeah, so if you have this, so going back from the hypercube to the ring, you just invert this function, so you have gray to binary instead. And this is, so if you want the left neighbor and the right neighbor, then, so this thing, gray to binary of the rank. Yeah, so gray to binary gives you this ring rank. -1 plus p mod p is your left neighbor. This part is your left neighbor in the ring. And binary to gray is just mapping it back into the hypercube. So this is like, you have a this is saying you have a hypercube rank R, and you're trying to find its neighbor from the ring. And vice versa, the right is just +1 in the index. So this is an example. Suppose you have this hypercube processor with rank 3. Its ring rank is 2. Its left neighbor in the ring is binary to gray of 1, because 1 is the left neighbor in the ring. Binary to gray of 1 is 1. And the right neighbor is binary to gray of 3, because you are 2 in the ring. You're trying to find the neighbors 1 and 3, and you map them back into the hypercube. The right neighbor is 2. Oops. Okay. So using this, you can extend it to higher dimensions. So in reality, like often we don't actually have just one-dimensional ring. We're more interested in like 2-dimensional and 3-dimensional meshes. Or yeah, so meshes is like the array form, and torus is the ring form of the higher dimensional thing. But yeah, so you can make these like 2-dimensional where you just kind of copy the array multiple times, and they're connected not only by the horizontal links but also by the vertical links. And the torus, the torus is the mesh with the wraparound. You can also do it in higher dimensions like 3. And we're going to focus on the case where the dimension length is always a power of 2. And the way that we're going to do that is just by extending. So we have a scheme to do it in 1 dimension. And we're just basically going to make a bit string that concatenates all the dimension bit strings. So in 2 dimensions, suppose we have this 2 to the r by 2 to the s wraparound mesh. We can map it. So there are 2 to the r, 2 to the power r plus s total nodes in this thing. This number of nodes, and we want to map it into a hypercube with this number of nodes. And we map node ij, so we can index the nodes in this mesh with row index and column index ij into the hypercube by concatenating the 2 binary to gray codes. So we have the binary, so like in the mesh, we have some index like 2, 1, and we map that into binary to gray. So like this index 2, 1 would in the hypercube become binary to gray 2 concatenated with binary to gray of 1. And that's why like binary to gray of 2 is 3 and binary to gray of 1 is 1. So you just concatenate these together. And it works in arbitrary dimensions. How does this? So we showed that the reflective scheme preserves the gray code property for one dimension. Is it clear that concatenating it works in arbitrary dimensions? You're saying yes. Why? Yes. So so you want this property. The concatenation needs to be unique. So you need to cover the entire space of the nodes, and also your neighbors. All your neighbors in arbitrary dimensions need to map to something only one bit away from you. And that is true because of the property of gray codes. If you move along one dimension, you're only changing the bit string in like the bits that correspond to that dimension. And because we generated them with gray codes, you know that stepping one in either direction in one dimension will differ only in one bit. So basically, this is the aggregation of the one-dimensional scheme just together, and each subpart of it corresponds to one dimension. So each subpart, like when you take one step in one dimension, only the part corresponding to that dimension will change. And we need that property because we're trying to map this whole thing into the hypercube. In the hypercube, the neighbors differ by only one bit. Mhm. Yeah, so it's a really good point, and we will actually get to it later. If the dimension of the mesh goes up to log p, actually it just degrades into the hypercube. Yeah, so yeah, it's a good point. Like the dimensionality is limited, but because like uh, the length of the dimension has to be at least 2, because otherwise, like if the length of the dimension is 1, there's no point. You might as well have gone to one less dimension. So the maximum dimensionality uh, of the mesh actually goes into hypercube, which we will talk about in a later lecture. Did I answer the question? Mhm. Yes. Yeah, I think for this mapping purposes, we're going to only focus on the case where um, there can be a one-to-one mapping in the nodes. And the maximum case of that is the hypercube. Yeah. So this is just more formalization about how you actually compute this. So the rank can be represented as a bit string of r plus s bits if you have 2 to the r by 2 to the s mesh. And the rank is concatenated x concatenated with y, where x is the first r bits and y is the last s bits, because you need r bits to represent to the r and s bits to represent to the s. And the mesh rank in the hypercube is just given by gray to binary. So yeah, so you have x and y in the hypercube, and if you want to go back, that's gray to binary. If you want to go forward, that's binary to gray. So this is how you get back the mesh rank from the hypercube rank. And this is just the same thing that we have been doing for like the left and the right step for the ring, except now since we have 2 dimensions, we have 4 neighbors, up, down, left, right. And this is how you calculate the right and the left, how you calculate the left and the right, or sorry, the top and the down, because if you go left and right, only the column changes, the row is fixed. So that's why the row is fixed here with x, and this column changes in this way. And vice versa, if you change the row with north and south, then the column is fixed, but the row changes. And this is just how you get back the, if you have the hypercube rank and you are interested in getting back the mesh rank. Yeah. And you can do it for, so this is like an example of how you do it in 5 dimensions. So you can just apply the scheme. We concatenated the bits, but you just concatenate the bits here. So this is like an 8 by 4 by 16 by 2 by 8. So that's 13 bits. But for 8, you need 3 bits. For 4, you need 2 bits. For 16, you need 4 bits. For 2, you need 1 bit. And for 8, you need 3 bits. These are just powers of 2. So you break down this bit string, like 3, 2, 4, 1, 3. And this is the mesh rank. And you generate this entire bit string by looking up the gray code corresponding to each subpart of the mesh rank and concatenating them together. Yeah, so we have these properties like congestion, dilation, expansion, and load. They are unaffected by going into higher dimensions, because if it worked for 1 dimension, like we still have the same properties. Every node is distinct in this mapping or in this embedding, and they also map to distinct edges. And they also map to only one edge in the embedding. So they're all one. Questions so far? We can stop for a second. Mhm. Mhm. Wouldn't it take time to compute those factors? This is just the size of the high dimensional mesh. That's given upfront. Oh yeah, sorry. So this is like the size of the mesh will be given upfront, and from here you can figure out how many bits each dimension will take, because it's just log the length of the dimension, and then you concatenate them all to get the total bit string. Other questions? Okay, great. So we can move on. So this part is briefly about performance differences that you get in mappings. So let's just consider broadcast for a second. How long would it take in a square mesh versus a hypercube? So like I said last time, when you have this mapping, it will preserve the time and the efficiency on the original source topology. It will not necessarily achieve the maximal efficiency on the target topology, but it will be, yeah, so it will be the same efficiency and the same runtime if it is truly a mapping, which is like everything is 1-to-1. You'll preserve the runtime. So how long does it take in a square mesh? In a mesh, it takes, assuming, let's say you have p processors and it's a square. So one dimension is root p. Then in the mesh, the broadcast operation would take root p time, because at least you have to go like from the upper left to the upper right or something like that. Or yeah, even if you propagate it in like a wave, you have to go at least the length of the dimension. So that would be root p. In a hypercube, however, it would take log p. Like if you had a broadcast algorithm directly on the hypercube, we know that we have algorithms that can take log p time. And the reason for that is because the mapping does not use all the edges in the hypercube. But that's okay. The reason so one convenient thing is that either at the end of this class or next class, depending on how far we get, we're going to do matrix algorithms on the mesh because it's easier to think of them that way. But sometimes in the matrix algorithm, you're interested in doing something like broadcast or reduce, and you would like to achieve the hypercube runtime rather than the mesh runtime for those primitives, because they're faster in the hypercube. So that's one reason that we're interested in simulating the mesh algorithms on the hypercube. But like it's hard to reason about the matrix algorithms directly on the hypercube because like partitioning a matrix onto the hypercube is way harder than partitioning it onto the mesh. So that's the reason for these embeddings. It allows you to translate the algorithms designed easily logically for one into the other. So the last part of embeddings is about binary tree topologies. So we just did so actually arrays and rings and like meshes are a very fundamental topology that are useful in a lot of cases. And binary trees are also useful in many cases. Like we have algorithms that are logically well suited to trees like broadcast or like many of the primitives have a tree-like fashion when you do the processors. And for example, so for example in broadcast or sometimes like for example in image processing, you can do parallel processing by cutting up the image into quadrants and doing subcomputation on the quadrants. And in that case, it's not a binary tree, but it's a four-array tree. So yes. Why is the broadcast square root of p in mesh? So if you have p processors, then the length of each dimension in the mesh is root p by root p. And you have to, let's say like in the worst case, you have to broadcast starting from the upper left, just through to all the nodes. You have to at least take one hop per node in each row, and the top row has root p length. So yeah, so in some cases we are interested in designing algorithms on binary trees, but again, we have like suppose that we have actually a topology that can run hypercubic permutations because as we have seen, like hypercubic permutations allow for these general algorithms. So now we're going to consider the source as binary trees and the target topology as a hypercube. Okay. So one first way that we can try to do this is if we have p leaves in the binary tree. So we have 2p minus 1 nodes. And suppose we have a 2p node hypercube. So we can definitely embed all the nodes. Like if we have enough nodes theoretically to do this one-to-one mapping, but we have to define some kind of function. And with that loss of generality, suppose that the root is mapped to a node with an even number of zeros. And we would like to have this property that all the neighbors in the tree are also neighbors in the hypercube. So in the tree, like if the root has an even number of zeros, its neighbors in the hypercube have an odd number of zeros. And in the next level, like the nodes with an odd number of zeros, neighbors have an even number of zeros because they all differ in 1 bit. So if something has an even number of zeros, all its neighbors have an odd number of zeros. So one possible assignment is like this. Suppose that the root has an even number of zeros, then every alternative level, like if the root is level 0, then level 2 and level 4, and so on like that, all have processors with even number of zeros if we try to maintain this one-to-one neighbor mapping. Then the entire leaf level is going to be mapped to targets, to processors with the same parity, either even or odd, depending on the height of the tree. And the number of such processors of this parity required is p plus p over 4 plus p over 16, and so on. However, we only have p with an even number. We only have p of each parity, like in the hypercube, or in any just general for binary things. Like if you have, you have like an arbitrary bit string, and half of the possible instantiations have an even number of zeros, half of the possible instantiation have an odd number of zeros. So with this initial assignment, we cannot do this mapping because there's not enough such processors. Is the issue clear? Yeah, and that hinges on the property that all processors in the level have the same parity. So maybe we can try to relax that. Right, we're gonna fix this assignment. One possible way is that hinged, so the initial way we're doing the simple assignment is we just assign the opposite parity in the next level. we can try to split between even and odd parity in every level. And that will work. However, the dilation would become 2 because you may have to go across 2 links rather than 1. Like, so if you, in the hypercube, if you have an even number of zeros, all your neighbors have an odd number of zeros. And to get to another node with an even number of zeros, you're going to have to take at least 2 hops. Unless it's you, but like, it's not you. So, um, yeah. And so the dilation would become 2 because in the tree, like if you are a node in the tree and your child has an even parity in the hypercube, then you're going to have, so yeah, if your child is assigned to something with even parity in the hypercube, in the tree that's distance 1, but in the hypercube it would become distance at least 2. So this is trying to split, this is trying to assign every node in the tree to a unique node in the hypercube. So one way that we can get around this is try to take advantage of the properties of the algorithms. So many of the algorithms proceed level by level, which means that like you process, the root process does something, and then in the next level, like its children, its logical children do something, and then after that, those logical children of that level do something. So yeah, and every level, the levels have to proceed sequentially, but the nodes in the levels can do the work in parallel. And so one idea is if you have an algorithm of that form, you can reuse some of the processor assignments between the levels. This is similar to like in the broadcast, we reused like the root processor, for example, like the root process participates in every level of the broadcast. So instead, how are we going to assign? So this is one way that we can get around this issue of the dilation is we can reuse the processor again here. So like, let's say 0, 0, 0 is the root. We set 0, 0, 0 also to its left child, and 1, 0, 0 to its right child. And similar, like we set 0, 0, 0 as the left spine all the way down, and the right child of this in the next level is just flipping the middle bit. So in this one, we flip the top bit. In here, we flip the middle bit, and also between these, we flip the middle bit. So the difference between 1, 0, 0 and 1, 1, 0 is flipping the second bit. And finally, in the last one, the difference between the 2 pairs of children is flipping the smallest bit. This is kind of similar to the hypercubic assignment that we did in broadcast, for example. Like the data starts on 0, and then in every round, like 0 sends to someone else, and as the algorithm goes on, like those algorithms can help, or those processors can help out in the broadcast, and they get reused in the different levels. So this is formalization. The tree has log p plus 1 levels, and the root is at level 0. And the way that you assign it into this hypercube, we can have this tuple where I is the height of the node, and j is the index. Yes, yeah. J is the index and that node, labeled 0 up to 2 to the I minus 1. Then the hypercube rank of any given node with this tuple is the first I bits are set to j, and the lower ones are set to 1. So for 0, the height is 0, I equals to 0, and it has one node, which is 2 to the I, and since just 1 is just 0. But like for level 1 has 2 nodes, because 2 to the 1 is 2, labeled 0 and 1. So that's like the 2 indexes, the height and the level within the node, or the index within the level. Yeah, so in this tree, this tuple ij is connected, so I is level, and it's connected to, at level I plus 1, index 2j and 2j plus 1. And this is how you would do the assignment. So given some node, its left child is just the same assignment. This is the same, like I bits and log p minus I bits. It's just exactly the same copy. And this part is different. We set 1 in this part in the lower half. And this is going to give us two different bits. Or sorry, this is going to give us different bit strings. And it will also give distinct bit strings along one level, because J is different for every node here. So similar to in broadcast, some processors may participate in multiple rank, or given your rank, some processors may participate in multiple levels of this algorithm. And yeah, and this is just the indexing. Questions? Yeah, so I think this is the last slide on embeddings, and we can move on to matrix algorithms. But just to recap a little bit, like when you have to do something like this in the exam, questions will be similar. Like you may have to convert like binary to gray or gray to binary. The questions are kind of similar to this form, something like this form, where either you have a mesh index and you need to compute the hypercube index, or you have a hypercube index and you need to compute the mesh index, vice versa. And you do it through this bit manipulation. So one thing that can be confusing is like the direction that you're trying to go. So just be careful, like which way is binary to gray and which way is gray to binary. So yeah, we can do matrix algorithms. Yeah, that was it. One second. Okay. Okay, cool. So we have about 20 minutes, and we're going to do matrix algorithms. So yeah, so we're not doing embeddings anymore, and all the algorithms that we're going to do for dense matrix algorithms will be logically run on either the mesh or the torus, but they're the same with the wraparound links. And the reasoning is because like when you have a 2D matrix, it is easy to think about it split up on a 2D grid, and it's hard to think about it split up on a hypercube. But because we have embeddings, we can achieve hypercube runtimes in the algorithms by just running the subroutines on the hypercube. So to recap, we're going to be using these communication primitives to design the algorithms. We have broadcast, reduce, and all reduce. Broadcast is you have one thing and everybody needs to get the one thing. Reduce is everybody has something and they need to aggregate it onto one processor. All reduce is everybody has something and they all need to get the aggregation. And scan is like prefix sum. And then we have gather, all gather, and scatter, which are more expensive than these broadcast, reduce, all reduce, and scan. So the runtime is here, this tau log p is the same, but this is mu m log p, and this is mu mp. M is the size of the message. And then we have two options for all to all, based on what kind of permutations the underlying architecture can support. So like in the homework or in the exam or anything, you don't have to remember these. Like I will give you these. So in the next exam, I'll just give you a sheet with all these runtimes. So you don't have to remember that, but you have to use them as building blocks in algorithms. So like if you're trying to reason about the runtime of an algorithm and you say, okay, like it's going to take an all reduce and a gather, for example, then you just add up the all reduce and the gather times. So we're going to do dense matrix algorithms, which have this nice regular structure. So dense matrix just means that we have a 2D matrix, and all the entries are actually there, which means like as opposed to sparse matrix, which is another active area of work. Sparse matrix means that many of the elements are empty, and we have specialized data structures and algorithms for that case, but we're going to do dense matrices first because those are easier to think about. And one nice thing about dense matrix algorithms is that they're well suited to static partitioning, which means that you can partition them upfront just based on the length of the dimensions. Like if you know your dense matrix is n by n, you can just cut up the pieces equally onto your grid. Yeah, the computation is usually partitioned based on the data. So you cut up your data, and that defines some partitioning of your algorithm, some problems in your algorithm. And yeah, so like you have an input matrix, sometimes you have an output matrix or a vector or whatever it is, and you may have some intermediate product. There are different kinds of data partitioning strategies, and we will go through some of them. Some really common ones are called like 1D and 2D, just based on which dimension you cut it along. There's also cyclic and block cyclic. Yeah. And it's easier to think about the algorithms on a 2D mesh, so we're going to do that. So the most basic dense matrix algorithm is matrix vector multiplication. And matrix vector multiplication is like this. We have an n by n matrix called A, and we want to multiply it with an n by 1 matrix, n by 1 vector x. And so we're going to get an n by 1 vector y out because the dimensions are like n by n, and then it's like n by 1, so the output is also n by 1. And so every entry in y is the dot product of one row of A and the entirety of x. So like we're going to do this, and then the second row is like this and that, so on. And the serial time complexity is n squared because every entry in A gets multiplied with something in x. Actually, every entry in x gets multiplied with, I guess the reverse is every entry in x gets multiplied with multiple things in A. It's like in the dot product. Every column touches the same element in x. Questions? Clear why the serial complexity is n squared? And it's clear like what the actual computation is doing. It's doing these dot products. So yeah, so we want to do it in parallel. And one easy way we can do it in parallel is just cut up the rows. So every row is independent from each other. Like theoretically, if you had P processors, you could do every single dot product in parallel. So that's just 1D partitioning, which means that we split the matrix along one dimension, which is the rows. And since usually P is less than n, we cut it up into block rows, where every partition is more than one row. But like if P was equal to n, then every partition would just be equal to one row, and all the dot products can proceed independently because all the outputs, each dot product corresponds to one entry in the output y. So you can do those all separately. Yeah. If you have n rows, you can use at most n processors with 1D partitioning because every processor has to do at least one dot product. And the different colors are just like if you have 4 processors, this is how you cut it up. Yeah. So that is 1D partitioning. Another way to cut up the matrix is called 2D partitioning. So in 2D partitioning, rather than cutting up just along the rows, you can also cut up along the rows and the columns. And 2D partitioning is a little bit more complicated because in 1D partitioning, like every dot product corresponds to one entry in y. But in 2D partitioning, now you have these partial dot products because we cut it along the columns as well. So like just look at the first row. It needs to aggregate this dot product with this partial dot product. And those are on 2 different processors. So at the end, somehow we're going to have to reduce along some dimension to get the total value in y of this first total dot product. But the good thing about 2D partitioning is that you can use up to n squared processors because now we cut in 2 dimensions and there are the minimum size of the input matrix that you can get is 1 if you cut along both dimensions, so that's why you can use up to n squared processors. Questions so far? So let's start with 1D partitioning. And let's consider the most simple case where P is equal to n. So every processor is going to do one dot product of one row of A and the entire thing of X. And so the n by n matrix gets partitioned on the P processors. Each processor is going to get one row of A, and each processor needs all of X to do the dot product. And in the initial distribution, let's say that X is also partitioned in a similar way, so each processor has one element of X. So with this initial partitioning, we cannot do the dot product in 1D because we need all of X on each processor, but we can just get it there. Which primitives would you use? Or you just need one primitive. Which primitive would you use to get X onto all the processors? All to all. Then maybe that one? Scatter? Each process has one element. You could do broadcast, like, because for example, like P0 needs to broadcast 0 to everyone, P1 needs to broadcast 1 to everyone, something like that. So so every process has one element, and in the end, all the processes need to have all the elements. You can do it through a sequence of broadcasts, that's true. There is maybe a better way. You can use gather. Is that what you said? You can use, maybe there's, yeah, all gather. So all gather is everybody has something, and in the end, after the all gather, all the processors have all the things. That makes sense? So all gather is just like an extended form of gather. In gather, everybody has something, and after gather, all those things are going to end up on one processor. And all gather is just an extended version where all the things will end up on all the processors. So yeah, so this is just an example, like how do you use these primitives to build actual algorithms? So just even in this simple 1D partitioning, we have to set up the vector X to get ready for everybody to use it. Yeah, so the first step, we use all gather to get all of X onto each processor. And the all gather time, we just plug in the hypercubic runtime, tau log n plus mu n. And in this case, m is equal to m, the message size is equal to 1. But here p equals to n, so that's where this n factor comes from. If you remember, the all gather runtime is tau log n plus mu m p. P is equal to n, m is equal to 1, and that's how we get that. And so once you have the vector x on each processor, everybody can serially compute the dot product. They all compute the dot products in parallel, but like on one processor, you sequentially compute one dot product. And that will take time n, because the dot product has length n. So the total time of this whole thing, you add up both of them, and the time is mostly in this all gather, because already mu n is greater than n, not even thinking about this tau log n factor. So the time is basically dominated by the all gather in this case. Any questions on this part? And yeah, so that is not ideal because the time was dominated by the all gather, whereas we want the time to be something like n squared over p. And so for now, so that was for p equals to n, and instead we're interested in the case where n is greater than p, because most cases the input size is greater than the number of processors. And so in this partitioning, rather than having one row, yes, yes, we're assuming that it has already been distributed. Yeah, for the previous case, we're assuming that the matrix has already been distributed, just row by row, and the vector has been distributed element by element up front. So we didn't need to do anything about the matrix because that was already fine. Oops. No, I was right. Okay. Yeah, so now we're going to go to the case where n is greater than p. So now rather than one row of A, every processor gets n over p rows of A. And every processor is going to get n over p elements of X rather than one element of X. Because there are n total elements in X and n total rows in A. So the number of elements that every processor has of A is n squared over p. Because every row has length n, and it has n over p rows. So we need to do a similar thing. Everybody still needs to get X, but now rather than doing one dot product, everybody can do n over p dot products if they have X. So we again do this all gather on the p processors, but now the messages have size n over p rather than 1. Because previously we were all gathering and everybody had one element of X, but now everybody has n over p. And then on each processor, we're going to do n over p local dot products. So rather than just doing one dot product, now we have n over p rows of A. And if you have all of X, you can just do all the dot products and you compute n over p elements of Y. So how are we going to analyze this? What is the communication time? Mu n. Yeah. Yeah. So tau log p is there. Mu. So this is m, and this is p. M is n over p. P is just p. They cross out, you get mu n. And the computation time? And how did you get that? Yes, good. So the computation time is n squared over p because everybody is doing n over p dot products, and each of those takes n squared over p time. Like to do n over p dot products takes n squared over p time because each one takes n time. And that's the computation time is like the maximum time that it takes any one processor to finish. And in this case, it's evenly distributed, so they all take about n squared over p time to finish. And in this case, so we have two steps. We have the communication and we have the computation. And we can use up to about n over mu processes because to get maximum efficiency, the computation time should dominate the communication time. And so if you set the number of processors equal to n over mu, then this thing is bigger. Or equal to up to n over mu, then this thing is bigger. Questions? Make sense? So like this is a common way that this analysis goes, which is like we have two components. One is communication time and one is computation time, and we analyze them somewhat separately. And ideally, it's a bit like if we analyze the computation right, ideally we would like to see something like the serial runtime over p, because the maximum if you have P processors, the maximum or the minimum time that you could spend to do it is work over P, serial work over P, because the maximum speed up is P. Yeah, so that's just one way to check, like, if you see something like serial work over P, then you probably did the computation time right, unless your algorithm is work inefficient. Yeah. So now we can move on to 2D partitioning and consider the simple case where P is equal to n squared. So we're going to partition this n by n matrix across n squared processors, and every processor gets one element. And every processor has one element, and then let's say the vector x is just distributed one element by one element on the last column of processors. Because we have n squared processors, and there's only n elements of x. So, given this, what is a good algorithm? So what is going to happen? Every row of processors needs to compute one dot product of a row of A. And to do that, every processor needs one element of X. And then at the end, you can reduce them. So this is the algorithm. We have this grid. Every one of them, every processor has one element of A, and they need to get one element of X. So we can align this vector along the diagonal because every column needs to get the same element of X. Because that's just the way the dot products are. So once you align them along the diagonal, you can broadcast along the entire column the element of X. Then you do this horizontal reduction along the rows. And then the vector Y, the elements are in the last column. The algorithm clear? Yes. The first step is just, so originally the vector X is just along the last, like every element is just one by one in the last column. And we need to get every element of X, like the first element of X needs to end up in the first column. The second element of X needs to end up in the second column because the way that the dot products are, it's like this. So the second element, the ith column multiplies the ith element of X. And so that's just the initial alignment to get them into the right columns, just by doing a single send. And then to get them everywhere in the column is to do broadcast. Mm-hmm. So matrix A is also split across the processors. In the beginning distribution, you have n squared processors, and every processor has one element of A. But there are only n elements of X, so they have to be in the initial distribution, like without copying upfront. There can only be n processors that have elements of X. Good question. Other questions on this part? Mm-hmm. Yes. Yeah, we're assuming the mesh topology. So yeah, you can see like um, it's easier to logically think of the matrix algorithms on the mesh topology because trying to do this distribution in the hypercube is a little bit complicated. But with the embedding, you can actually get the hypercube runtimes. Like even the all-gather runtime that we just used is using the hypercube runtime, which we do with the embedding. I think I'm out of time, so we can continue this next time. Thank you.